There are three types of bonds: single, double, and triple. A single bond, you have one pair of electrons being shared. It's the lowest in energy and the longest bond length. Double bonds, you have two pairs of electrons being shared, and a triple bond, you have three pairs of electrons being shared. It's the strongest of the bonds because it's also the shortest of the bond lengths. Sigma and pi bonds make up those single, double, and triple bonds. A sigma bond is formed from the overlap of orbitals in the plane between atoms, while a pi bond is formed by the overlap of unhybridized p orbitals above and below the center plane. You do not have to know the definitions of sigma or pi bonds, but what you do need to be able to do is recognize them in a molecule. So a single bond is simply a sigma bond. So all single bonds are sigma bonds. A double bond consists of one sigma bond, and the other one is going to be a pi bond. In a triple bond, you're going to have one sigma, which is the middle one, and the other two above and below it are your pi bonds. In other words, every bond has a sigma bond. All additional bonds are going to be pi bonds. So here's an example where we're trying to count how many sigma and pi bonds are in this molecule. This is a very complicated molecule, so if you could do this one, you should be able to count sigma and pi bonds in any molecule. Go ahead and try figuring out how many pi bonds are in this molecule, and then restart when you've got just the pi bonds. So your pi bonds, you should have said, was 6. Every double bond, one of the lines for the double bond was a pi bond. So that's 1, 2, 3, 4, 5, 6. Which means all the other bonds are going to be sigma bonds. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So 27 sigma bonds and 6 pi bonds. Here's another one where you're trying to figure out your sigma and pi bonds. The thing that makes this one a little bit tricky is the first thing you've got to do is redraw this molecule so you can see the sigma and pi bonds. To do so easily, I would count the number of carbons. I have 1, 2, 3, 4, 5, 6, 7, 8. And I would draw that carbon skeleton. 1, 2, 3, 4, 5, 6, 7, 8. On the first carbon, I have 3 hydrogens. At the end of each of those lines is a hydrogen. You can draw the hydrogens, but it is understood to be a hydrogen by just leaving it as a line. The next carbon has 2 hydrogens. Notice that adding those 3 hydrogens and 2 hydrogens is giving carbon 4 bonds. Carbon has to have 8 electrons when it's bonding, and so this satisfies the octet rule. Our third carbon has 2 hydrogens. Our fourth carbon has 2 hydrogens. Our fifth carbon has only 1 hydrogen. Our sixth carbon has no hydrogens, and then the last one has 2 hydrogens. So notice these 2 carbons do not have 8 valence electrons currently. So to do so, I would need to add a double bond. And then this carbon only has 3, so it also needs a double bond. So that's 1, 2, 3, 4. This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3. Needs another double bond. And then 1, 2, 3, 4. So this would be the Lewis structure for this condensed formula. Go ahead and pause the video and figure out how many sigma and pi bonds are in this Lewis structure that we just drew. If you said 19 sigma and 3 pi, you are correct. So our 3 pi were 1, 2, 3. All the other lines that we drew were our sigma bonds. Make sure that you have this structure drawn in your notes. So now we're going to talk about resonance. If you see from the cartoon, it says define resonance. Sure, that's where you live. That's not the type of resonance that we're going to be discussing. In chemistry, resonance occurs when more than one valid Lewis structure can be written for a particular molecule. Our example is NO3-1. So go ahead and pause the video and draw nitrate on your own paper. Make sure that you don't use that entire box, so draw it on the left-hand side of the box provided. So nitrate had 24 valence electrons. So you should have seen that you needed a double bond to draw nitrate. Don't forget that you needed brackets and a -1 charge. So nitrate has resonance because if you look at the structure that you drew, maybe you didn't put the double bond on the left-hand oxygen. Maybe you put it on the bottom one or the one on the right. All of those are valid. Also, from our discussion at the beginning of the video, we said that double bonds are shorter than single bonds. Therefore, I would expect this bond to be shorter in length than this bond and this bond. I would expect 2 long bonds and 1 short bond. But that's not what occurs in nitrate. When they measure the bond lengths, due to resonance, all of the NO bonds are the exact same length and they're all exactly the same strength. They're between a single and a double bond. Because that's not the structure that exists, it's a hybrid of all of the resonance structures. So to represent resonance, you have to draw all of the resonance structures that are possible. In this case, there's 3 different structures. Between the structures, you need a double-headed arrow. So here we can see that the double bond's not on the left or the bottom or the right. It's a hybrid of all 3 of these. That double bond is spread between the 3 bonds, making it longer than a double bond, but shorter than a single bond. Make sure that you understand the concept of resonance and how it applies to bond length and bond strength. The next and last topic we're covering is formal charge. So in formal charge, our equation is the number of valence electrons on the free atom. In other words, how many did it come in with? Minus the number of valence electrons assigned to the atom in the molecule. To get the valence electrons assigned, you're going to say that it's all the lone pairs it has, so all the electrons that are in lone pairs plus half of every shared electron. And we'll see this formula in action in a second, and it should make more sense once you see it. 2 things that you need to have for a good formal charge is the sum of the formal charges must equal the overall charge on the atom or ion. And the particle is more stable with lower formal charges. If it must have a charge, the most electronegative element should be the one that's negative. Formal charge is used to decide which Lewis structure is the most stable for a compound. So for sulfate, there's 2 different ways of drawing sulfate. I have Lewis structure 1 and Lewis structure 2. The prompt would say which Lewis structure is the most probable Lewis structure based on formal charge. Explain why. So to calculate my formal charge, on A, Oxygen came in with 6 valence electrons. So that's the number of valence electrons on the free atom. Oxygen came in with 6. Minus, how many does it currently have? Well, it currently has 1, 2, 3, 4, 5, 6, 7. Because that center bond, or that bond, is 2 electrons. But it only has 1 for itself. So half of every line, it gets 1. So 6 minus 7 is a negative 1. Then sulfur came in with 6 valence electrons. Minus, how many does it currently have? Well, it currently has 1, 2, 3, 4. So that's a 2. For my oxygen, this one would be a negative 1. This one is exactly the same, so it would also be a negative 1. This one would be a negative 1, and this one's a negative 1. I didn't have you calculate the formal charge for all the oxygens because if you look, they're all exactly the same. They have 6 electrons that are lone, and they all have 1 bond. Then the sulfur in the middle has a positive 2. If you add that up, you get a negative 2, which was our overall charge. So from our criteria, we said the sum of the formal charges must equal the overall charge on the atom or ion. Check. So looking at our second molecule, oxygen came in with 6, and it currently has 1, 2, 3, 4, 5, 6. So 6 minus 6, that's a formal charge of 0. This oxygen is different, so I need to calculate it. It came in with 6, and it currently has 1, 2, 3, 4, 5, 6, 7. So that's a negative 1. This oxygen is exactly like C, so it's a 0. This oxygen is exactly like D, so it's a negative 1. And then sulfur, just like before, came in with 6. And sulfur currently has 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. Notice if I add these all up, I get negative 1 and negative 1 gives me negative 2. So it also has a sum of the overall charge, but the particle that's more stable has the lower formal charges. So if I compare these, molecule 2 has the lower formal charges, therefore it would be the more stable. With formal charges, I would never have you draw molecule 2, nor would the AP test. So you know it's a formal charge problem because they're going to say formal charge in the prompt. So when justifying two structures, make sure that you're showing your work on how you're getting these formal charges. You can't just say molecule 2 has smaller formal charges. You have to actually list the formal charges out. So here we have xenon trioxide, and we have 4 different molecules. So first, go ahead and calculate your formal charge for each of the letters represented. Restart when you have your formal charges. So for letter A, it was oxygen. It came in with 6 valence. Minus, it currently has 1, 2, 3, 4, 5, 6, 7. You should have gotten a negative 1. For xenon, xenon is a noble gas. It came in with 8 valence electrons. Minus, it currently has 1, 2, 3, 4, 5. So that's a positive 3. Going over to number 2 and C, oxygen came in with 6. It currently has 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. This oxygen on the bottom came in with 6, and it currently has 1, 2, 3, 4, 5, 6, 7. So that's a formal charge of negative 1. And then xenon came in with 8. and it currently has 1, 2, 3, 4, 5, 6. So that's a formal charge of positive 2. If you struggled on these two, go ahead and pause the video and try 3 and 4 if you haven't already finished them. So for number 3, F, it's oxygen. It came in with 6. And it currently has 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. G, oxygen, came in with 6. And it currently has 1, 2, 3, 4, 5, 6, 7. So that's a negative 1. And then H, xenon, came in with 8. And then that's 1, 2, 3, 4, 5, 6, 7. So that's a positive 1. Then the last structure, for oxygen, it came in with 6. It currently has 1, 2, 3, 4, 5, 6. So that's a 0. And then xenon came in with 8. 1, 2, 3, 4, 5, 6, 7, 8. Formal charge of 0. So if you had to choose what would be our best structure, 4 would be our best structure because every element had a formal charge of 0 compared to the others. Go ahead and pause the video and figure out your formal charges for A, B, C, and D, and then which structure would be the better structure based on those formal charges. For A, you should have had oxygen came in with 6. It still has 6. 1, 2, 3, 4, 5, 6. So it has a formal charge of 0. And then B came in with 6. And it has 1, 2, 3, 4, 5, 6. So formal charge of 0. We didn't calculate carbon, but carbon came in with 4. And it has 1, 2, 3, 4. So it also has a formal charge of 0. On structure 2, oxygen came in with 6, and it currently has 1, 2, 3, 4, 5. So that's a positive 1. And then D came in with 6, and it has 1, 2, 3, 4, 5, 6, 7. So that's a negative 1. And then our carbon came in with 4, and it currently has 4, so it has a formal charge of 0. So if I had to choose between structure 1 and structure 2, I would say structure 1 because the formal charges are smaller or lower than structure 2. And make sure that you have your work showing all of your formal charges. Here's some more practice for formal charges. Go ahead and do A, B, C, and D's formal charges. Restart when you're done. Structure A, carbon had 4. It currently has 4, so it had a formal charge of 0. So 1, 2, 3, 4. Oxygen came in with 6, and it currently has 1, 2, 3, 4, 5, 6, 7. So that's a negative 1. C is hydrogen. Hydrogen came in with 1, and it currently has 1, so that's a formal charge of 0. Oxygen came in with 6, and it currently has 1, 2, 3, 4, 5, so that's a positive 1. And then the last 4 of the formal charges, go ahead and pause the video and do these 5 on your own. Restart when you've got these 5. So for E, oxygen came in with 6, and it currently has 1, 2, 3, 4, 5. So that's a 1. Carbon came in with 4, and it has 1, 2, 3, 4. So that's a formal charge of 0. G is representing carbon. Carbon came in with 4 valence, and it has 1, 2, 3, 4. So that's a formal charge of 0. H is oxygen, so it came in with 6, and it has 1, 2, 3, 4, 5, 6. And finally, I is oxygen, so it came in with 6, and it has 1, 2, 3, 4, 5, 6, 7. So that's a -1. Sometimes on the AP test, you'll be asked to complete a Lewis dot diagram given a skeleton such as shown in the box below. In the box, it says, make sure that the molecule has the lowest formal charges and show all valence electrons. So just like we did before, you're going to want to make sure that everything has its octet filled, or octet/duet, and that you're only using the valence electrons you started with. So to do so, I would say, well, carbon had 4, 4, 6, 4, 6, 1, 1, 1, 1, 1, 1. Or I can say basically that was 10, 20, 24, 25, 26, 27, 28, 29, 30. In other words, you have 30 valence electrons to work with to satisfy the octets. So I know I have to connect all of the atoms, so that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 10 left. My hydrogens are all satisfied with the duet rule. This carbon has 8 valence. This carbon has 8. This oxygen needs some, this oxygen needs some, and hydrogen is good. And carbon still needs 2. So if I just put lone pairs, I would need 2, 4, 6, 8, 10, 12. But notice I only have 10 left. So I can't just do lone pairs. I'm going to need a double bond somewhere. If I put the double bond there, I would have 2. This carbon's now good, so 2, 4, 6, 8. That would work. So let me check my formal charges because it specifically said check your formal charges. This oxygen would have 6 minus 1, 2, 3, 4, 5. That's a positive 1. And then this oxygen would be 6 minus 1, 2, 3, 4, 5, 6, 7. That's a -1. So those aren't zeros. They don't have to be zeros, but it's more likely to be correct if they're zeros. So the other place we could have added a double bond would be between this C and O. So now I still have 8. If I add my lone pairs, everything has 8 just like it did before, but now when I check my formal charges, oxygen came in with 6. It currently has 1, 2, 3, 4, 5, 6. That's a formal charge of 0. And this oxygen came in with 6, and it currently has 1, 2, 3, 4, 5, 6. That's a formal charge of 0. So this must be my correct structure. So doing that helps with this answer. It says, does this molecule have resonance? We're going to say no. It does have a small degree of resonance because that double bond could go where we had placed it beforehand. But because the formal charges aren't as low as they are in this structure, very little of the molecule would actually have that resonance. So for our purposes, we're going to say no, it does not have resonance because the majority of the molecule would not have resonance. If we could have put that double bond on the left, how we had it a second ago, and the formal charges would have been 0 both ways, then yes, it would have had resonance. Go ahead and pause the video and figure out how many sigma and pi bonds are represented in this molecule. If you said it had 1 pi bond and 10 sigma, then you are correct. There was our 1 pi bond. And then all the other lines were our sigma. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you're confused on the resonance piece, if we look back at our nitrates, notice that it doesn't matter which way I move the double bond, the formal charge would always be the same. If you calculate the formal charge in all the molecules, this one, it would have a formal charge of -1. This one would be a 0, and this one would be a -1, and this one's a +1. But that's going to be the case in all of these. I have my -1, -1, 0, +1, -1, -1, +1, -1, and +1. So notice the formal charge isn't changing. It's the exact same formal charges in every molecule. I can't get a 0 all the way across, or just where one atom has a -1. Go ahead and pause the video and try finishing the Lewis dot diagram in the box below, just like we did before. Restart when you have your answer. So you should have calculated your valence electrons. If you're not doing this step first, you're more likely to make a mistake. So make sure that you're calculating how many valence going into the problem. Then you have to connect them all. So 2, 4, 6, 8, 10, 12, 14, 16. I have 2 electrons left. All the hydrogens are satisfied. This carbon has 8, this carbon has 6, and this carbon has 6. Well, I only have 2, so I would add lone pairs, but I would need 4 to do so. Since I do not have enough electrons, I have to share more. I wouldn't put my double bond there because notice this carbon was already satisfied. So this makes carbon have 10, which it can't have. I can't put the double bond there because hydrogen can't have a double bond. I'd put it between the 2 carbons. Now each carbon has 8 electrons. So this is your final structure. So then ask yourself, does this have resonance? If you said no, you're correct. Although it has a double bond, I just shown that there's no other place that I could have put that double bond. So how many sigma and how many pi? If you said 1 pi and 8 sigma, you are correct. There's my pi bond. And 1, 2, 3, 4, 5, 6, 7, 8. Those are my sigma bonds.